Last episode, we hunted local extrema of f of x, y over the wide open plane, find the critical points where the gradient of f equals the zero vector, then classify them with the Hessian determinant. Today, we changed the rules of the game. Instead of optimizing f over the whole plane, we optimize it only on a curve, the constraint set g of x, y equals c. The unconstrained minimum of f might not lie on that curve at all, so we cannot just look for the gradient of f equal to the zero vector and hope. We need a new condition. The condition, due to Lagrange in 1788, is one of the most elegant equations in all of calculus. At every smooth constrained extremum, the gradient of f is parallel to the gradient of g. That is, the gradient of f equals lambda times the gradient of g for some scalar lambda. Together with the constraint equation, that's three equations and three unknowns, x, y, and a scalar lambda itself, called the Lagrange multiplier. We'll see why this works geometrically, what lambda actually means physically and economically, and we'll grind through two clean examples until the method feels automatic. First, the setup. We have a smooth objective function f of x, y that we want to maximize or minimize, and a smooth constraint function g of x, y that pins us to the level set g of x, y equals c for some constant c. So we're not free to roam the whole plane, we're stuck on the curve g equals c, and we want the highest or lowest value of f along that curve. This shows up everywhere. Engineers want the largest cross-section of a beam subject to a perimeter budget. Economists want the utility maximizing bundle, subject to a budget constraint p sub 1x sub 1 plus p sub 2x sub 2 equals capital I. Geometers want the closest point on a curve to a fixed point. All constrained optimization. Notice that the unconstrained method, set the gradient to 0 and classify, can completely fail here. The unconstrained critical points of f might not lie on the constraint curve at all, in which case they tell us nothing. Or f might have no unconstrained extrema yet have perfectly nice constrained extrema. Example, f of x, y equals x has no critical points anywhere, but on the circle x squared plus y squared equals 1, its maximum is x equals 1, and its minimum is x equals -1. The constraint creates the extrema. Here is the picture that makes the whole method obvious. Imagine the plane covered in level curves of f. Think of them as contour lines on a topographic map, each curve labeled with a height k. Now draw the constraint curve g of x, y equals c on top of that map. As you walk along the constraint, you cross level curves of f one by one. Each crossing means your value of f is changing, going up or down depending on direction. The maximum or minimum of f along the constraint happens exactly where you stop crossing level curves, where the constraint curve is tangent to a level curve of f. At such a tangency point, an infinitesimal step along the constraint doesn't change f to first order, which is exactly the constrained version of f is flat. And now use last episode's punchline. The gradient of f is perpendicular to the level curves of f, and the gradient of g is perpendicular to the constraint curve g equals c. Two curves are tangent if and only if their normal vectors are parallel. So at the constrained extremum, the gradient of f is parallel to the gradient of g. Two vectors are parallel exactly when one is a scalar multiple of the other. That scalar is lambda, the Lagrange multiplier, the gradient of f equals lambda times the gradient of g. Here is the picture. The blue branches are level curves of f of x, y equals xy. The hyperbolas xy equals k, with solid curves at positive k and dashed curves at negative k. The gold circle is the constraint x squared plus y squared equals 1. Watch what happens as you walk around the circle. You cross blue level curves with smaller and smaller positive k as you head out toward x equals 1, y equals 0, then you cross dashed, negative k, level curves as you head into the fourth quadrant. The maxima of xy along the circle are exactly the points where the circle stops crossing blue curves, where the circle is tangent to a blue level curve. The picture shows one such tangency point in the first quadrant, where the circle just barely grazes the highest k blue curve it can reach. At that point, look at the two gradients. The gradient of f is the vector with components y and x, and the gradient of g is the vector with components 2x and 2y. The first point's perpendicular to the blue level curve. The second point's outward from the circle, perpendicular to it. Because the curves are tangent, the two normals align. The Lagrange multiplier, lambda, is whatever scalar makes the equation the gradient of f equals lambda times the gradient of g true at that point. By symmetry of the picture, the gradient of f and the gradient of g both point along the diagonal direction, the vector with components 1 and 1, so they're manifestly parallel. Here is the formal statement, the heart of the method. Suppose f and g are smooth, and the constraint gradient, the gradient of g, is non-zero on the constraint curve. This is the technical condition called constraint qualification, and it guarantees the curve g equals c is a genuine one-dimensional curve at every point, not degenerate. Then, at every local maximum or local minimum of f on the constraint set, there exists a scalar lambda called the Lagrange multiplier, such that the gradient of f equals lambda times the gradient of g. That's a vector equation in two components, so it's two scalar equations, f sub x equals lambda times g sub x and f sub y equals lambda times g sub y. Add the constraint g of x, y equals c, and you have three equations in the three unknowns x, y, and lambda. Solve the system and you get a list of candidate points. The candidates include all the constraint extrema, but might also include boundary points or non-extremal critical points, so you typically classify the candidates by directly evaluating f at each one and comparing. The constraint qualification, the gradient of g not equal to the 0 vector, is usually trivial to check, but you should always check. If the gradient of g vanishes somewhere on g equals c, the Lagrange method can silently miss an extremum that lives at that degenerate point. First worked example. Maximize f of x, y equals xy on the unit circle x squared plus y squared equals 1. Compute the gradients. The gradient of f is the vector with components y and x, and the gradient of g equals x squared plus y squared is the vector with components 2x and 2y. The Lagrange condition, the gradient of f equals lambda times the gradient of g, gives two scalar equations, y equals 2 lambda x, and x equals 2 lambda y. Together with the constraint x squared plus y squared equals 1, that's three equations in three unknowns. Here is a classic Lagrange trick. Multiply the first equation by the second. Y times x equals 2 lambda x times 2 lambda y, which simplifies to xy equals 4 lambda squared xy. If xy is non-zero, we can divide by it. 1 equals 4 lambda squared, so lambda equals plus or minus 1/2. We should also check the excluded case xy equals 0. If x equals 0, then from y equals 2 lambda x we get y equals 0 too, and the point 0 doesn't satisfy the constraint x squared plus y squared equals 1. Same with y equals 0. So the xy equals 0 case contributes no candidates. The only solutions come from lambda equals plus or minus 1/2. Now solve both cases. Case 1, lambda equals 1/2. The equation y equals 2 lambda x becomes y equals x. Plug y equals x into the constraint x squared plus y squared equals 1, we get 2x squared equals 1, so x equals plus or minus 1 over the square root of 2. The two candidate points are 1 over root 2, 1 over root 2, and negative 1 over root 2, negative 1 over root 2. At both points, f equals x, y equals 1/2. Case 2, lambda equals negative 1/2. Now y equals negative x, and again the constraint gives 2x squared equals 1, x equals plus or minus 1 over root 2. The two candidates are 1 over root 2, negative 1 over root 2, and negative 1 over root 2, 1 over root 2, both with f equals negative 1/2. For candidate points, only two distinct values of f. The unit circle is compact and f is continuous, so by the extreme value theorem there must be a global maximum and a global minimum. The largest of our candidate values is 1/2. The smallest is negative 1/2. So the maximum of xy on the unit circle is 1/2, attained on the diagonal y equals x, and the minimum is negative 1/2, attained on the anti-diagonal y equals negative x. The picture from 2 slides ago is now fully labeled. The level curve xy equals 1/2 is tangent to the unit circle in the first and third quadrants. xy equals negative 1/2 is tangent in the second and fourth. Second worked example, a clean one. Find the point on the line x plus 2 y equals 5 closest to the origin. Closest means minimum Euclidean distance, but minimizing distance is the same as minimizing squared distance, and the squared version f of x y equals x squared plus y squared has nicer derivatives. So the objective is f equals x squared plus y squared. The constraint is g equals x plus 2y equals 5. Gradients, the gradient of f is the vector with components 2x and 2y. The gradient of g is the vector with components 1 and 2. The constraint gradient is constant because g is linear. The Lagrange equations, the gradient of f equals lambda times the gradient of g, give 2x equals lambda and 2y equals 2 lambda, so lambda equals 2x and lambda equals y. Set them equal, y equals 2x. Plug into the constraint x plus 2 times 2x, which is 5x, equals 5, so x equals 1 and y equals 2. The closest point is 1, 2, and the distance is the square root of 1 squared plus 2 squared, which is the square root of 5. Sanity check, this matches the standard point line distance formula, which gives the absolute value of 0 plus 0 minus 5, over the square root of 1 squared plus 2 squared, which is 5 over the square root of 5, which is the square root of 5. The geometric picture, level curves of f, are circles centered at the origin. The line x plus 2y equals 5 is tangent to the smallest such circle that reaches the line. At that tangency point, the radius vector, the gradient of f over 2, equals x, y equals 1, 2, points along the direction the vector with components 1 and 2, which is the gradient of g, gradients parallel. Now, what does lambda actually mean? It is not just an algebraic auxiliary to be solved for and discarded. The Lagrange multiplier has a deep and useful interpretation. It equals the rate of change of the optimal value of f with respect to the constraint level c. Let me explain. Suppose we wiggle the constraint. Instead of g of x, y equals c, look at g of x, y equals c plus delta c for some small delta c. The optimal f value will shift to some new f star of c plus delta c. The claim is that the rate of change, df star dc, evaluated at the original c, equals lambda. The proof is one line. Write f star of c equals f of x of c, y of c, where x of c, y of c is the constraint optimum as a function of c. Differentiate using the chain rule, df star dc equals the gradient of f dotted with the vector x prime, y prime. Apply the Lagrange condition, the gradient of f equals lambda times the gradient of g. This becomes lambda times the gradient of g dotted with x prime, y prime, which by chain rule again is lambda times the derivative of g with respect to c, which is lambda times 1. So df star dc equals lambda. In economics, lambda is the shadow price of a constraint. If you're maximizing utility subject to a budget, lambda tells you how much extra utility you'd get per extra dollar of budget. In physics, lambda is the generalized force conjugate to the constraint. If the constraint is stay on the surface, lambda is the normal force the surface exerts. The multiplier is the marginal value of relaxing the constraint by 1 unit. Always physically meaningful, never just notation. Let me show you the sensitivity interpretation in action with our line example. We found lambda equals 2 at the optimal point 1, 2. The claim is that the optimal value of f equals x squared plus y squared changes at rate 2 as we increase the constraint level c. Let's verify. Replace the constraint with x plus 2 y equals c for general c. By the same Lagrange algebra, the optimum lies on y equals 2x, the constraint becomes 5x equals c, so x equals c over 5 and y equals 2c over 5. The square distance is the quantity c over 5 squared plus the quantity 2c over 5 squared, which is c squared over 25 plus 4c squared over 25, which is 5c squared over 25, which is c squared over 5. So the optimal value function is f star of c equals c squared over 5. Differentiate, df star dc equals 2c over 5. At c equals 5, that's 10 over 5, which is 2, which matches lambda exactly. So if I shifted the line outward to x plus 2y equals 6, the square distance to the origin would increase from 5 by approximately lambda times delta c, which is 2 times 1, which is 2, giving roughly 7, and indeed 6 squared over 5 is 7.2, close enough for a first-order prediction. The Lagrange multiplier is not just a number that drops out of the algebra, it tells you the local sensitivity of your optimum to the constraint. One last extension, important enough to flag even if we don't grind through an example. Sometimes you have more than one constraint. Imagine optimizing f of x, y, z subject to two constraints, g equals c sub 1 and h equals c sub 2. Each constraint cuts a surface out of three-dimensional space. Together they intersect in a curve. We want the extremum of f along that curve. The Lagrange condition generalizes cleanly. At a constrained extremum, the gradient of f is a linear combination of the two constraint gradients. The gradient of f equals lambda times the gradient of g plus mu times the gradient of h, with two multipliers, one per constraint. Add the two constraint equations, and you have 5 equations and 5 unknowns, 3 coordinates plus 2 multipliers. The geometric story is the same as before, lifted by one dimension. The gradient of g and the gradient of h span the normal plane to the constraint curve, the plane of directions perpendicular to the curve. At a constrained extremum, the gradient of f has no component along the curve itself. Otherwise, you could increase or decrease f by walking along the curve, so the gradient of f lies entirely in the normal plane. Saying the gradient of f lies in the span of the gradient of g and the gradient of h is exactly the equation the gradient of f equals lambda times the gradient of g plus mu times the gradient of h. Same idea, more multipliers. A short history note. The method is due to Joseph Louis Lagrange, the Italian-French mathematician who lived from 1736 to 1813 and was published in his 1788 treatise Mécanique analytique. Lagrange's original setting was not abstract optimization but constrained mechanics. He wanted equations of motion for systems where the particles are forced to lie on a surface or curve, a bead on a wire, a pendulum, a body sliding on a sphere. The naive Newtonian approach requires you to figure out the constraint forces, the normal force from the wire or surface, explicitly, which is often awkward. Lagrange's brilliant move was to introduce auxiliary variables, his original multipliers, whose role is precisely to enforce the constraint. The constraint force is then lambda times the constraint gradient directly. This same algebraic trick, lifted out of dynamics and applied to static optimization, is what we use today. The preface to Mécanique analytique famously declares, "I propose to reduce the theory of this science and the art of solving the problems related to it to general formulas." And he meant it. The book contains no figures. Pure formulas, a complete unification of mechanics, and a lambda that has been quietly shaping optimization, mechanics, and economics for over 2 centuries. Time to compress the method into a cookbook you can apply on autopilot. Step 1. Compute the two gradients, the gradient of f and the gradient of g. Step 2, write the Lagrange system. The gradient of f equals lambda times the gradient of g, which is two scalar equations, plus the constraint g equals c as a third. 3 equations, 3 unknowns, x, y, and lambda. Step 3, solve. The usual tricks: divide one equation by another to eliminate lambda in terms of x and y, multiply pairs of equations together to get something symmetric, or just brute force solve for lambda and substitute. Step 4, check the constraint qualification. The gradient of g should be non-zero at every candidate, and add any boundary points or degenerate points where the gradient of g vanishes, because Lagrange can miss those. Step 5, evaluate f at all candidate points and compare. The largest value is the constrained max. The smallest is the constrained min, at least when the constraint set is compact and the extreme value theorem guarantees both exist. And remember, lambda at the optimum is the marginal value of the constraint. If you change c by a small delta c, the optimal f changes by approximately lambda times delta c. 5 steps, a gradient parallelism condition, and a free sensitivity number. Recap. The constrained optimization problem: maximize or minimize f of xy subject to a side equation, g of x, y equals c. The geometric insight: the level curves of f are tangent to the constraint curve at the optimum, which means the gradient of f is parallel to the gradient of g. Algebraically, this becomes the Lagrange condition. The gradient of f equals lambda times the gradient of g, paired with the constraint to give 3 equations and 3 unknowns, x, y, and the Lagrange multiplier lambda. We worked 2 examples. The maximum of xy on the unit circle is 1/2, attained on the diagonal y equals x at plus or minus 1 over root 2, plus or minus 1 over root 2, and the closest point on the line x plus 2y equals 5 to the origin is 1, 2 at distance the square root of 5. We learned that lambda is not algebraic noise. It is the sensitivity of the optimal value to the constraint level, the shadow price. Multiple constraints generalize cleanly. The gradient of f equals lambda times the gradient of g plus mu times the gradient of h. And the whole method goes back to Lagrange's 1788 Mécanique analytique, where it was invented to handle constrained variational problems in classical mechanics. Next episode, we leave optimization entirely and start integrating functions of 2 variables over regions in the plane. That's double integrals. That's Lagrange multipliers. One gradient condition, the gradient of f parallel to the gradient of g, captures the entire geometry of constrained optimization. The level curves of f kiss the constraint curve at the optimum, and the multiplier lambda that makes the gradients line up is also, bonus track style, the marginal value of the constraint. 5 steps, 3 equations, and a built-in sensitivity analysis. If this helped, like, subscribe, and post a comment with your answer to today's challenge. Find the dimensions of the rectangular box of maximum volume that can be inscribed in the sphere x squared plus y squared plus z squared equals 3. Set up f of xyz equals xyz as the volume of the box with corner at xyz in the first octant. The full box has corners at plus or minus x, plus or minus y, plus or minus z, so its volume is 8xyz, but the multiplier analysis is the same. Constraint: x squared plus y squared plus z squared equals 3. You should find a cube. Next episode, we change gears completely. So far, we've been asking where a function f of xy is biggest or smallest. Next time we ask, how much of f is there over a region? We chop the region into tiny rectangles, multiply f times area, and add up the contributions. That's the double integral, and it brings us into the second great chapter of multivariable calculus: integration over surfaces, lines, and volumes. See you there. Given a smooth objective f of xy and a smooth constraint g of xy equals c with del g is not equal to 0 on the constraint set, the Lagrange condition says that at every smooth constrained extremum there exists a scalar lambda in R such that del f of xy equals lambda del g of xy equals c. Geometrically, the level curves of f are tangent to the constraint curve at the optimum. The gradients are parallel. The number lambda is the Lagrange multiplier, and it carries real meaning. Lambda equals df star dc, the rate of change of the optimal value f star as the constraint level c shifts. We'll solve the 3-equation system in 2 clean examples: the max of xy on x squared plus y squared equals 1, and the closest point on x plus 2y equals 5 to the origin, and discuss the extension to several constraints, where del f equals lambda del g plus mu del h traces back to Lagrange's variational mechanics. Next episode, we change topic entirely. We stop asking where f is biggest and start asking how much of f there is over a region. That's the double integral. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.